All right. In this lesson, we will talk about sigma notation and limits of finite sums. That is really important notation to calculate um, the sum of, infinite terms. So in the previous class in 5.1, actually, we just talked about area and estimating with finite sums. And in that case, if you remember, if you're given any irregular region, right, we just divide it into smaller regions, and that means that we just actually try to fill this region with very thin rectangles. And as we increase the number of rectangles, our estimation gets better and better. Now, to get the exact area of this region, actually our n should go to infinity, which means that we need to find the limit of the partial sum. Partial sum is sum, right, which has n terms. So now today we are going to talk about sigma notation and limits of finite sums. How we are going to use sigma notations? And sigma notation is just very compact way of representing the sum. And after that, limits of finite sum. And after getting some, let's say, the taste of this definite integral, then we are just going to give the definite integral definition. And you will see that after that also we are going to see a few examples, maybe 2, 3 examples. And you will see that actually every time evaluating definite integrals using a definition will be really, really tedious job. And after that, actually, then we have to think if there is any shorter and faster and more convenient way to calculate this definite integral. And after that, actually, we are going to prove this fundamental theorem of calculus, which is, let's say, the most powerful and the most useful theorem in calculus, which actually makes a bridge or connection between differentiation and the integral. Okay, anyway, now we are going to talk about sigma notation and limits of finite sums. So number one, what is finite sums and what is sigma notation? What are the properties of the sigma notation and limits of finite sums and the Riemann sums? That's what we're going to talk about in this class. Now let's start with the definition of finite sums and sigma notation. Finite sums means that it has countable number of terms, right? That's 1, 2, 3, 4. You see here n terms. We can see this. That's why finite sums. Infinite means that it goes to infinity. Now we are using this capital letter. They call this sigma in Greek alphabet. The sigma, under the sigma, we have k is equal to 1 to n. Actually, is a count of, what is it? Index or counter. It's just counting here. And this a sub k, that's our function. So this k is equal to 1. And at the top of this sigma notation, we have n. That means that this k is changing from 1 to n. That means it's just actually taking on all the values between 1 and n. K equals 1. And we have to evaluate the value of this a sub k. And plus k is equal to 2. A2 plus A3 plus A4 plus AM. Simply, how do we actually represent or denote this sum? A1 plus A2 plus A3 plus N. We have N terms here in a compact notation. Mathematicians introduce this sigma notation to represent this sum. Okay, what is this k here? This k index k starts with at k equals 1, and this n, the index k, ends at k is equal to n. So this a sub k is a kind of function here. A sub k is a formula for the kth term of this, let's say, kind of sequence. Let's say we are given a number sequence and we are just adding up is terms. Some examples. Suppose if you are given this sum, 1 squared plus 2 squared plus 3 squared plus dot dot, that's 17 squared. How can I write, or how can I how to say label this or present this sum using a sigma notation? To do this one, since we have 17 terms, right, that means that this k takes on 17 different values, so consecutive positive integers. It doesn't have to be positive integer, but if it starts with 1, that means that k actually takes on the values from 1 to 17. 1, 2, 3, 4, 5, 6, 17, k squared. So that is one compact way of representing this sum. If k is equal to 1, we have 1 squared plus k is equal to 2, 2 squared plus 3 squared plus dot dot until 17 squared. So the index k changes from 1 to 17. And how about if we are given a function and we have to add its values at 300 different points, right? At 1, x equals 1, at x equals 2, and x equals 3, and dot dot dot, x equals 300. So how do I write this sum in compact form? Because we cannot write all the terms, right? And of course, I can just write with this dot, but in calculation, writing in sigma notation is more convenient. So to do this one now, let's say our index is j. J is equal to 1 to 300. That means j is changing from 1 to 300. F of j, right? We are just evaluating the value of this f at every value of j and adding them up. F of 1 plus f of 2 plus f of 3. Another example, express the sum. 1 plus 3 plus 5 plus 7 plus 9 plus 11. How do we express this? Using sigma notation. First, you have to actually count the number of terms. Here we have 1, 3, 5, 7, 9, 11. As you see here, they are odd numbers, right? And what is the general term of odd number? Any odd number can be expressed either as 2 times n plus 1 or 2 times n minus 1, right? And now I can just express every term as 2 times k minus 1. And I can write here k change from 1 to, what is it? When it is 6, right? 2 times 6 is 12. 12 minus 1 is 11. It gives us 11. So k change from 1 to 6. See here we have 6 terms. Now I can just write this, the sum. Let me just label this by s. So here we have 1 plus 3 plus 7 plus 9 plus here we have 7 plus 9 plus 11. Another example for finite sum. So here we have sigma, and our index starts with 1. K is equal to 1 to 6. Now, what is our formula? Here, our formula is 2 times k minus 1. Okay. So now you see here, if k is equal to 1, 2 times 1 minus 1, it is 1. If k is equal to 2, 2 times 2, it is, what is it? 4 minus 1, it is 3. And k is equal to 3, and dot, dot, dot. And algebraic or algebra rules for finite sums. It is exactly the same as the properties of addition, right? So now sum rule. So if we are talking about two number sequences and their general terms are a sub k and b sub k, and we are just adding these number sequences. We are talking about two sequences. Let's say 1, 2, 3, 4, 1, 2, 3, 4, right? How can I add this? We have to add their corresponding terms, right? The first term with the first term, and the second term with the second term, and the third term with the third term. Or I can just sum the first number sequence, the terms of the first number sequence, and the terms of the second number sequence, and add them up together, right? And that's why here we have sigma notation, and a sub k plus b sub k is the same as the sum of the terms of the first number sequence plus the sum of the terms of the second number sequence. And how about the difference rule? Actually, addition and difference, the same thing here. Also exactly the same, just we have to change plus into minus. And how about the constant multiple rule? So here we have c times a sub k, right? So that's equal to c times sigma a sub k. Why is it so? To just see this every time, just you need to not to forget this quickly. You have to actually consider one simple example. Now, if you consider this, suppose that we are given a sigma and k is equal to 1 to 3. And let's say here we have 3 times, what is it? K. Okay, so what is this? This one is when k is equal to 1, 3 times 1. When k is equal to 2, 3 times 2. When k is equal to 3, 3 times 3, right? Every time I see here, this 3 appears in our products. So 3 is a common factor. I can write it as 3 times 1 plus 2 plus 3. Or again, this 1 plus 2 plus 3, I can write it with sigma notation. Here we have sigma, k is equal to 1 to 3, and here we have k. And that's why if we multiply the general term, the sequence by some constant, right? We can just take this outside or out of this sigma notation. It means that we can factor this out. And how about here? We have k is equal to 1 to n c, and here we have n times c. Sorry, here we have constant number that's equal to n times c. Okay. So what does it mean? It means that actually here our function a sub k, right? In the last one, in this case, actually our constant general term of the sequence that is equal to 1, right? Here we have c times a sub k, and that's equal to 1, because whatever here we have k is changing, but this one is not changing. And that's why when we actually write this in long notation, so here we have c times 1 plus when k is equal to 2, again this c times 1. When k is equal to 3, again c times 1, and dot, dot, and the last one will be c again times 1, right? And how many terms do we have here? We have n terms here. And that's why the sum is equal to n times c. Let's see some examples. Just examples, I mean, to apply the rules. Okay, we are not going to calculate this yet. After proving three important sum formula, then we will start evaluating or using this sum to calculate, to find the area of some regions. Apply the algebra rules for finite sum for the following sums. So using the first one, this one, I can just write as sigma. And here we have k is equal to 1 to n. And here we have k squared plus, and sigma, also this 3, right? I can just write 3 in front of the sigma notation. And sigma k is equal to 1 to n. And here we have k. And soon we are going to learn how do we calculate this sum. What is this sigma? K is equal to 1 to n, k squared is equals. So how about the next one? Here, this -1, right, is multiplied by -1. So I can write as minus and sigma. Here we have k is equal to 1 to n, and here we have k. K is changing here, so I have nothing to do. And how about this 2k plus 5? Again, using that property, I can write it as the first one, right, 2 times k. 2 is a constant number, so it is 2. And here we have sigma k is equal to 1 to 5. And here we have k. And plus also 5, right? I can just write 5 here. So it is, what is it? K is equal to 1 to 5. And here we have 5. And see here, this part that's equal to, what is it? This part is equal to just 5 times 5. That's 25, right? And I can simplify this further. So here 2 times sigma k equals 1 to 5. And here we have k. That is 5 times 5. That's equal to 25. In similar way, now we have just seen the last formula, right? 1 over n, and k actually taking value from 1 to n. So this sum is equal to what? It is 1 over n times it is n, right? So this sum is equal to 1. Because 1 over n plus 1 over n plus 1 over n, because this n does not depend on k, right? What is changing here? K is changing here. So how many 1 over n's do we have here? N. That's why its sum is equal to 1. All right, now guys, everybody should, actually I want to say must, but if I say must, it may be a little bit harsh, but you should know the next three formulas are very commonly used formula in math, and also actually we are going to use them to calculate some, to find the area of some, what is it, non-regular regions. Okay, before this first we have to make sure that this formula is true, and then we can use them. And of course, not everybody should prove this, but especially if I'm sure that there are a lot of students here in this group who have passion for math, okay? So if you're interested, you can prove it for yourself. It really improves your thinking skill and the way that you look at things, right? And also your, what is it, creative skill. So now, how are we going to use this one? On the left-hand side, let me just label this by S, n. Actually, we call this partial sum. So that is Sn, right? That means that we are just adding the first n terms of, or n natural numbers, right? So what is this k equals 1 to? And k is changing. This means that it is k equals 1. Yes, it is 1. K equals 2, it is 2. K equals 3, it is 3. K equals 4, it is 4, dot, dot. And k is equal to n, it is m. We are just adding the first n natural numbers. Now to prove this one, let me just label this Sn by S. First, let me just write it as 1 plus 2 plus 3 plus dot, dot, dot. And here we have, let's say, n minus 1 plus n. Okay. Now, in math, we know that we have very simple, what is the identity? A plus B is equal to B plus A. That means that if you just replace the addends here, right? If you're adding two numbers, A plus B is always equal to B plus A. And using this property, if I just write this sum in reverse order, then I will get this thing. This S is equal to, the last one is, here we have N. The previous one is N minus 1. The previous one will be N minus 2, dot, dot. And here we have 2 plus 1, right? Now, if you just add them side by side, so here we have S plus S, that's equal to 2 times S. And 1 plus N, it is N plus 1. And the 2 plus N minus 1, again, it is N plus 1. And 3 plus N minus 2, again, it is N plus 1, dot, dot. And the last term, again, it is N plus 1. But actually, how many terms do we have here? We have N terms, right? So we are just actually adding n terms here. We have n terms here. So 2s then is equal to, here we have n, what? N plus 1. Now, if I divide both sides by 2, then we will get this sum formula. So this s, which is sigma, and k is equal to 1 to n. And here we have k, that's equal to n times n plus 1 over 2. Another important formula. What is it? The sum of the squares of the first n natural numbers. That is 1 squared plus 2 squared. As you see here, sigma k is equal to 1 to n, right? K squared. That is the sum of the squares of the first, what is it? N natural numbers. So here we need to find simply what is s. This, let me just label this as that our s is equal to 1 squared plus 2 squared plus 3 squared, and here we have n squared. What is this sum? And now this actual theorem is saying that sum is equal to n times n plus 1 times 2n plus 1. Okay, so we are just going to make a quick proof of this sum. And before we start the proof, actually you have to remember that here we have a plus b cubed, right? That's also one of the frequently used identity in math. A plus b cubed is equal to a cubed plus 3 times a squared b plus 3ab squared plus b cubed. And the second one is the difference of the squares of two numbers, right? That is a squared minus b squared, can be factorized as a minus b times a plus b. And now I'm just going to use this to get something. What is that? How about if you just actually consider this? Here we have n plus 1 cubed minus n cubed. That's equal to, here we have n cubed plus 3n squared plus 3n plus 1 minus n cubed, right? And this n cubed, they cancel each other. We have only this term, okay? So now keeping this in mind, all right, now let me start with, what is it, n. So if n is equal to 1, what happens here? On the left-hand side, let me just write here in purple. So if n is equal to 1, so on the left-hand side, I have this formula. On the right-hand side, I have 3n squared plus 3n plus 1, right? So what do we have here? If n is equal to 1, here we have 2 cubed minus 1 cubed. On the right-hand side, 3 times 1 squared plus 3 times 1 plus 1. And how about if n is equal to 2? 2 plus 1 is 3. So here we have 3 cubed minus 2 cubed is equal to 3 times 2 squared plus 3 times 2 plus 1. So on this dot, right? And how about if n is equal to 3? At the time here we have 4 cubed minus 3 cubed. That's equal to 3 times 3 squared plus 3 times 3 plus 1, right? So now if I just keep writing this in this way, when n is equal to n, right, at the time here we will have, what is it? N plus 1 cubed, n plus 1 cubed minus n cubed will be equal to, on the right hand side, we have 3 times n squared plus 3 times n plus 1. Okay, so next thing is, now I'm just going to add the left-hand side to the left-hand side, all left-hand side, we're just going to collect them, and also right-hand sides. Now, if I just add all of them together, what happens here? If you notice here, this 2 cubed, right, with 2 cubed, it will be actually canceled, and it will be gone. And 3 cubed and 3 cubed, also it is gone. 4 cubed and 4 cubed, also it is gone. And here we have n cubed and also n cubed, also it is gone. So what do we have on the left-hand side here? Only this term, right, and 1. So on the left-hand side, I have here n plus 1 cubed and the minus 1 cubed, that's equal to 1. And how about on the right-hand side? If you just add this term by term, let's see here, let me highlight this. So actually here we have 3 and 3 and 3, all of these 3's, they are common terms, right? And 1 squared plus 2 squared plus 3 squared plus dot dot n squared. That's I'm looking for this, right? And we have already labeled this by capital S. So I can just write here, this 3 is a common factor. And here we have 3 and bracket. And here we have 1 squared plus 2 squared plus 3 squared plus dot dot dot. And here we have n squared plus, And the second term, right, 3 times 1 plus 3 times 2 plus 3 times 3 plus dot 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 3 times n. Again, 3 is a common factor. Let's factor out this 3. Inside the brackets, here we have 1 plus 2 plus 3 plus dot dot, and here we have n. And plus, how about ones? How many lines do we have here? As we here starting with 1, right? 1, 2, 3, 4 until n. So we have n ones. So the sum of all these ones is equal to, what is it? It's just equal to n. Now, if I just rewrite this and I have to simplify this, right? I'm going to find this s. So let me just rewrite this here. N plus 1 cubed minus 1. If you simplify this, I have here n cubed plus 3n squared plus 3n. And 1 minus 1, it is gone. And 3 times, what is the sum of the squares of this one, the natural numbers, right? 1 squared plus 2 squared plus 3 squared plus dot dot n squared, that I'm looking for this sum. And I have already labeled this by capital S. So let me write capital S here. And plus 3 times. And how about the sum of the first n natural numbers? We have just proved this in our previous slide. That's equal to n times n plus 1 over 2. And plus I have n. So now I have to solve this equation for s, right? So just keeping this 3s on the left and take everything else to the right-hand side. What do we have here? So here we have 3s will be equal to n cubed plus 3n squared plus 3n, and the minus, and here we have 3 over 2 n times n plus 1 minus n. And see here, n is a common factor. And after that, if you just simplify this, it's just algebraic manipulation. If you simplify and factorize, you will get this sum. So this s will be equal to, and also divide both sides by 3. We will get an n times n plus 1 times 2n plus 1 over it is 6. Okay. So that is how we prove this sum. And the next important formula is, what is it? The sum of the cubes of, let me just write here, the sum of the cubes of the first, what is it? Natural numbers. So that our s is equal to 1 cube plus 2 cube plus 3 cube plus 4 cube plus dot dot, and here we have n cube. Okay. One way to prove this one is, of course, we have some different ways, but I'm not going to talk about the general way here. But one simple way is, let me just label here, here's Sn, okay? So now if you observe this one, what is S1? We have only one term, that is 1 cubed, that's equal to 1, right? And how about S2? S2 is equal to 1 cubed plus 2 cubed, that's equal to 1 plus 8, that's equal to 9. And next one is S3, that's equal to 1 cube plus 2 cube plus 3 cube. That's equal to 1 plus 8, 9. 9 plus 27. 27 plus 9 is, what is it? 36. I can write maybe one more. S4 is equal to 1 cube plus 2 cube plus 3 cube plus 4 cube. You will see that is 64 plus 36. That's equal to 100, right? So if you notice here, all of these sums, they are perfect squares, right? Or simply square numbers. So actually, they are not scores of consecutive integers, positive integers, but actually they are just scores of triangular numbers. Triangular numbers means that, for example, 1 or 3 or 6, right? Or what is it? 10. And these are triangular numbers. Why? Because, for example, if by using 1 dot or 3 or 6 or 10 or 15 or 21, I can form a beautiful triangle. That's why they are called triangular numbers. So actually, what is 1? 1 is equal to 1 times 2 over 2. Actually, the sum of the first number, right, squared. How about 9? It is 3 squared. That is 2 times 3 over 2 squared. And how about 36? It is 3 times 4 over 2 squared. And how 100? It is 4 times 5 over 2 squared. And now if you see here, actually, it's just revealing some kind of pattern here, right? 1 times 2 over 2, 2 times 3 over 2, 3 times 4 over 2, 4 times 5 over 2. Now looking at this pattern, I can make actually a good educated guess here. So S5 then will be 5 times 6 square over 2. And S6 will be 6 times 7 over 2 squared, right? S8 will be 8 times 9 over 2 squared. So now, actually, after this, I can use mathematical induction method to prove this one. Now, we suppose that actually this sum is true for when n is equal to k, or when k is equal to n. So if I can prove the same thing for when actually k is equal to n plus 1, so it is done, okay? But this one, actually, I'm not going to use this method now. I will focus on just using this formula to find the area of the region, which is bounded by some, what is it, nonlinear curves. Now let's start with the first example. And once again, I will suggest every student to do at least 2 examples, okay? Because I'm going to ask one question in the final exam, how to evaluate, or even in the quiz 5, how to do this using this method. And you have to get the taste of this initial approach to the definite integrals. Otherwise, you'll never be able to, how to say, have any kind of intuition about this definite integrals. Anyway, we have seen this example in our first example, right? In the previous session, or what is it? We estimated the area under this curve, right? By drawing some rectangles. Maybe in the first case, actually, lower bound means that all rectangles were inside this region. And also we draw some other rectangles where it just completely covers this, and some parts are lying outside this region. Anyway, we have estimated this. Now we'll try to find the exact area of this region using our method, because now we know the how to find the final sum, right? To do this one, let me just start here. Okay, to do this one, I am going to divide this. What is it? The base, right? The integral from 0 to 1 into n subintervals. Okay, what is the question here? Find the limiting value of lower sum approximations to the area of the region. Here is saying the lower sum, right? Are below the graph of this and above the interval 0, 1 on the x-axis using equal width rectangles whose width approach 0 and whose number approach infinity, right? To do this one, let me just show you only one of them. Okay, here, for example, it says lower sum, right? Maybe I can just draw one rectangle here. Okay. All right. So yeah, we are drawing a lot of rectangles. One of them will be something like this. Okay, something like this. So it says that the lower sum, right? So lower sum means that I am using this rectangle to estimate this area. Okay, which is under this part. Actually, this part, right? This part. So to do this one, actually just divide this into n, right? So this point will be x k minus 1. And how about this point? This point will be x sub k. And how about this delta x? Delta x, let me just write here, this equal space, right? So our delta x is equal to x k plus 1 minus x sub k over this n, right? And since actually the length of this one is equal to 1, right? Delta x is equal to 1. So simply, we're just dividing, what is it? Dividing this 1 into n sections. All right. So let me just write like this. If I draw here, so that's our line segment, and this one is 0, and this one is 1, right? And I have just divided this into n equal length. So that is the first one, and the second one, and third one, and fourth one, and fifth one, and blah, blah. That equal space, right? We have a lot, right? And what is the length? I'm just talking about the first one of them, right? So that is delta x. And since I have divided into n equal subintervals, right, it will be 1 minus 0, the length of our line segment, and divided by 3. Okay. So now if I just write, actually, what is it? The coordinates of these points. The first one, right? The first one is here, what is x sub 0? X sub 0 is equal to 0, right? And how about x1? X1 is equal to 0 plus 1 over n. And how about x2? X is equal to 0 plus 2 times 1 over n, right? So you have to jump 2 times to reach this one. That is one, actually, this one is, let me just write here, this one is x sub 0. This one is x1, x2, x3, x4, x5. And It just continues like this. Okay, and this part is really important to form our suitable sum, suitable partial sum. Otherwise, you will not be able to evaluate this. What is it? Area. Now, let me just label, okay, this area by, let's say this A sub K. Okay, then what is my A sub K? That's a rectangle, right? That's a rectangle is equal to the width times height. And what is our height? Height is this part, right? See here, this one is height. Height is equal to the value of the function at this point. That's equal to f of x sub k, right? So that's equal to height. That is f of x sub k times width. And what is width? Width is delta x. Now, if I just substitute the values, right, and I know our function. Our function is, once again, if you just write here, this x sub k will be equal to 0 plus k times 1 over n. So f of x k, right, that's equal to f of xk means that here we have f of k over n times, and how about this delta x? Delta x is equal to 1 over n. And we know our function, right? Our function is given as, what is it? Y is equal to 1 minus x squared. So 1 minus x squared, and that's equal to, so here we have 1 minus x. That's x sub k. What is x sub k? That is our x input value here. It is k over n. And here we have squared, right? And still we have here what? Here we have 1 over n. Okay. And let me just simplify this further. Okay, then we will evaluate. So if you just remove the brackets here, I have 1 over n minus, and here we have k squared over, and here we have n squared times n. Here we have n cubed. Okay. That is the area of one rectangle. But since actually we have divided this into n subintervals, then let's just say the area of this one is S, right? And then the area of this shaded region will be approximately, right? Approximately, we are not sure yet. So that is the sum of all the areas, right? K is equal to 1 to n. And here we have, what is it? This A sub k. All right. So what is this A sub k? That is sigma. And k is equal to 1 to n. A sub k I have just found here. That's equal to 1 over n minus k squared over n cubed, right? And now using our, what is it? The skill, we have just actually did a few examples about using the sigma notation, right? I am going to evaluate this one. Going to evaluate what? Now I assume that as I increase the value of this n, which means that as n goes to infinity, right? And it gives us actually better and better and better approximation of the area of the shaded region, which is actually enclosed by the graph of this function and the x-axis and y-axis, right? So that means that what I'm looking for here is I need to find this s. What is s? S is equal to limit as n goes to positive infinity, and here we have sigma, and k is equal to 1 to n a sub k. Okay, and soon actually I'm going to label this part, this sum. Actually, we are going to call this, we are going to give a special name soon. Okay, we're going to label this as s sub m. That is actually our partial sum. Anyway, now you need to focus on this part, the sigma part. That's 1 over n minus k squared over n squared and cube, right? I'm going to evaluate this. How? I'm going to rewrite this again. Okay, so first I'm going to evaluate. So here we have, first let me simplify. Then actually after that, I'm going to, what is it? Evaluate it is a limit. So Sn is equal to, let's see here, first we have 1 over n. So here we have sigma using the properties of sigma. K is equal to 1 to n. And here we have 1 over n, 1 over n minus, again, here we have sigma. K is equal to 1 to n, right? What we have here, k squared over n cubed. So here we have k squared over n cubed. Okay. And before actually I continue before I evaluate its limit, let me simplify this sum. This sum is equal to what? So I have to bring this into the form so that I can evaluate its limit, right? So that's equal to now 1 over n and the sigma, right? We have just done this earlier. So that's equal to just 1, because 1 over n plus 1 over n plus 1 over n, because n is not dependent on k. What is changing here? K is changing here. So actually this sum, that's equal to just 1. So here we have 1 minus, and this n cube again, it's not dependent on k. What is changing here is k. So here we have 1 over k n cube times, and here we have the sigma. K is equal to 1 to n, and here we have k squared, right? And also we have just proved here the sum of the squares of the first n natural numbers. So that's equal to 1 minus 1 over n cubed times, what is this sum? This sum is equal to n times n plus 1 times 2n plus 1 over n 6. Okay, so now I'm going to evaluate this limit. Again, before this, let me just write this in a suitable way so that it will be easy to calculate this limit. So that's equal to 1 minus, so this n, it is gone, right? So here we have n plus 1 over n times, and here we have 2n plus 1 over n. Because in the denominator, we have n squared. But still, I have 1 over 6, right? So let me just write here 1 over 6, here 1 over 6. Okay, now if I just rewrite here 1 minus 1 over 6 times, what is n plus 1 over n? We can write it as 1 plus 1 over n times, how about 2n plus 1 over n? That is 2 plus 1 over n, right? So now we can find the exact area of this region. So that S is defined as limit as n goes to positive infinity, and here we have that partial sum. We are going to call this Riemann sum soon. So that means that here we have limit as n approaches positive infinity. And what is this Sn? That's equal to 1 minus, not plus, it is minus, 1 minus 1 over 6 times 1 plus 1 over n times and 2 plus 1 over n. Okay, right? And we know how to calculate this limit in chapter 2, right? So really easy limits. So that's equal to 1, it is constant. That's equal to 1 minus 1 over 6 is also a constant number. And 1 plus 1 over n, it is 1 over n 0, right? So here we have 1 times 2 plus 1 over n, that's equal to 2. So that's equal to 1 minus 2 over 6, which is equal to 1 over 3. Or that area is equal to 2 over 3. So the area of the shaded region is equal to 2 over 3, right? Now you will see that actually it's a long procedure using the definite integral. If we know the relation, right, how definite integral is connected to differentiation, in 1 or 2 steps we can get this. But to get to that point, you have to feel this burden. You have to feel this, how tedious it is, right, to come to this result. And that's why this forced mathematicians to find some easier and a more mathematical or rigorous way. How can we evaluate this area in a simpler, more convenient, faster way? Then actually, so they, how to say, discovered that fundamental theorem of calculus, okay, and after that everything, speed up. Or let's say we say that just this discovery fueled the development of math, that is 17th or 18th century during that Newton's time. Anyway, guys, we have that's it about this calculation. Okay, now we are going to talk about this special sum, because every time I cannot say this partial sum. This partial sum has a special name. Okay, that is Riemann sums. Riemann is George Frederick Bernard Riemann. It is one of the great mathematicians from Germany who lived between 1826 and 1866. Okay, he is the one who introduced this method. All right. So now suppose that we are given some function, continuous function over the interval AB, that y is equal to f of x. Let me just change the laser. Okay, y is equal to f of x. That's the graph of the function. Okay, so a over b. So now we are going to introduce one important concept, because very, very important concept for indefinite integrals. It is to form a Riemann sum. How are we going to form a Riemann sum? Okay, see here, this function is defined over the interval, closed interval AB. Okay, so now we are going to choose, all right, let's say n minus 1 points inside, or interior points, or inside this AB. Okay, so here x1, x2, x3, x4, dot, 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 xn and 1, xn minus 1. So we just choose n minus 1 points. And just for convenience, we are going to choose or label the first point as x sub 0. A, the first endpoint, by x sub 0. The other endpoint as x sub m. You don't have to do that. It's just for convenience. So at the time, as you see here, this given interval AB would be divided into n subintervals. Now, they don't have to be equally spaced, or these intervals, or the length of these intervals, they don't have to be equal to each other in any way you can choose, okay? Just we are dividing this into n subintervals. You see here, a is less than x1, x1 is less than x2, x2 less than x1, in such a way that actually it's well ordered, right? Because this x2 is to the right of x1, and x3 is to the right of x2. So to make the notation consistent, we denote a by x sub 0 and b by x sub n, so that we have this notation. Then the sets. Now x sub 0, x1, x2, xn minus 1, x sub n. How many points here we have? Xn plus 1, right? Is called a partition of the line segment AB. Okay, it's a kind of special term here. How are we partitioning here? In this way. So it's called the partition of AB. The partition P divides the line segment AB into n closed subintervals, right? As you see here, from x sub 0 to x1, the first subinterval. From x1 to x sub 2 is the second interval. From x sub 2 to x sub 3, this third interval, right? So from k minus 1 to x sub k, right? X sub k minus 1 to x sub k, that is k subinterval. Again, the length of these intervals, subintervals, they don't have to be equal to each other, okay? And that's not actually a condition for us. It can be anything. Of course, for even if it is equal space for to calculate the definite integral, the result does not change. And that's why we are going to choose the easiest way to do this one. That usually, if it is equal space, it will be easy to calculate, okay? And since the result does not change, we have to choose the easiest one. So the first of these subintervals is x sub 0 to x1. The second one is x1 to x2, right? The third one is x2 to x3, and so on. And now we are going to choose a point from the interval x sub k minus 1, x sub k. That is kth interval, right? If you look at this one, x k minus 1 and xk, right? I just choose any point lying in this interval, okay? So it may be, maybe you can choose, for example, x sub k minus 1. Or you can choose this point, for example. You can choose this point, or you can choose this point. It doesn't matter. So what is important here is this point belongs to this line segment, okay, the subinterval. And after that, here we, as you see here, we are evaluating the value of the function f of sub k and multiplying the value of the function by the length of this subinterval. That's delta x sub k. It is the length of this, what is it? The length of this subinterval, right? So the sum, this SP, is called the Riemann sum for f on the interval AB. Okay, this is how we are forming the Riemann sum. So this sum SP, okay, is called, what is it? The Riemann sum for the function f on the interval AB. Okay. So we have some examples. You have to practice at least 1 or 2 examples to understand this concept, all right? And in our next class, we're going to talk about the definite integral, all right? Thank you.